Hi guys, I wanted to talk to you about a couple of quick ideas for our exponential functions. The first thing that we're going to look at is writing a function from a table. This is going to be really similar to when we wrote our explicit formulas for our geometric sequences and when we wrote exponential functions at the beginning of our unit. And then we're also going to talk about exponential growth and decay as a percentage or as a rate. So we're going to start by writing exponential functions from a table. So if I take a look at my table here, I've got my x values, I've got my f of x or my y values. So notice that my x values are increasing by 1, so 0, 1, 2, 3. Notice that my y values go 7, 14, 28, 56. Remember, for an exponential function, I'm always multiplying by something to get to the next term, and I should be multiplying by the same number each time. 7 times 2 gives us 14. 14 times 2 gives us 28. 28 times 2 gives us 56. So I'm going to need a point from my table, and I'm going to need this, what we call growth factor. So if you remember in our notes, we use this y equals a times b to the x as sort of a generic version of our exponential function. I use the same thing here to write a function based on my table. So my y value when x is 0 is going to go in front. That would be 7 times. And then my growth factor here, or my rate of growth, my rate of increase in this case, goes as the base for my exponent. So this would be 7 times 2 to the x. The other tables I have are oriented a little bit differently, but I see the same thing. My x's are increasing by 1s. So now I want to select a point from here and figure out what's my rate of growth. So 4 times 3 gives me 12. 12 times 3 gives me 36. 36 times 3 gives me 108, and so on and so on. So my exponential function that describes this table would be y equals 4 times 3 to the x. And then one last example here for table C. Again, my x's are increasing by 1. My y's go 5, 15, 45, 135. So 5 times 3 gives me 15. 15 times 3 gives me 45, and so on. I'm going to grab that first point from here, and my function would be y equals 5 times 3 to the x. So writing a function from a table means that we're going to pick out a point from that table and identify that rate of either growth or decay. When I have a function already, we can identify the rate at which we're growing or decaying as a percent. Now, this is something that we haven't done in class yet, but we're going to see coming up here. So the big idea here is to determine whether our function represents growth or decay, and then to find that percent of increase or decrease. If we have exponential growth, the base for our exponent would be greater than 1. So 2 or 5 or 1.04. If we take a look at our functions here, each of these that we wrote had a base for the exponent greater than 1. These were all growth. That should make sense because every time our y value got bigger, as our x value increased, so did our y. So we were growing our functions. So if the base for my exponent is greater than 1, that's growth. If the base for my exponent is less than 1, that's decay. Okay. So if I take a look at my problems here, for D, the base for my exponent is greater than 1, so this is growth. And then to find that percent of increase or decrease, what I'm really asking is what's the change from 1? So 1.05 has a 0.05 difference from 1. 0.05 as a percent would be 5%. So this is a 5% increase. For E, same idea. We're looking at the base of our exponent. I don't care what number's in front. I just care about the base of the exponent. For e, the base of our exponent is greater than 1. So this is, again, exponential growth. And then our percent of increase in this case is, again, related to that difference from 1. So if I look at 1.668 and I look at its difference from 1, I get a difference of 0.668. Move that decimal 2 places, write this as a percent, and that would be a 66.8% increase. For f, same idea. I'm going to look at the base of my exponent. Since this number is bigger than 1, it's growth. Now, it's not a lot bigger than 1, so that means we're not growing very quickly, but it's still bigger than 1, so it's still growth. And then again, I'm going to look at that difference from 1. So this time that difference would be 0.004. Move my decimal 2 places, and I have a 0.4% increase. Now for our bottom line here, again, I'm looking at the base for my exponent. Notice for g that the base for our exponent is less than 1. So that means this is decay. Again, I'm going to look at, to find that percent, I'm going to look at the difference from 1, but 1 is bigger than 0.95. So I'm going to subtract 0.95 from 1 this time. And I get a 0.05 difference from 1. So that would be a 5% decrease. Since it's decay, that means the amount we have each time is decaying, decreasing. Okay. So 5% decrease because there's a 5% difference from 1. For h, same idea. I'm going to look at the base of my exponent. This is less than 1. So this again would be decay. To find the percent I'm decreasing each time, I'm going to find my difference from 1. So this would be a 0.98 difference from 1. If I move that decimal 2 places, I have a 98% decrease. So a pretty substantial decrease each time. And then for our last example here, same idea. I'm going to look at that base of the exponent. Since this number is less than 1, that means that this is exponential decay. And then I'm going to look at my difference from 1 to determine the percent of decrease. And again, since this number is less than 1, I'm subtracting it from 1. And so we would get 0.252 this time. Move my decimal 2 places, and we have a 25.2% decrease. Okay, that's it for today.